Okay, this section is dealing with partial fraction decomposition, but before I get into that, I want to kind of show you the reverse of that, something that you're familiar with. So suppose it gives us this problem here, right, as a single fraction. Then we want to use common denominators to combine this together. So the common denominator here would be x plus 1 and x minus 2. So if I wanted to get common denominators, what I would do is I would multiply each one by what is missing here. So I would do x minus 2 over x minus 2 here. It's missing that one. The other one has x minus 2, but it's missing the x plus 1. So I'm going to go ahead and multiply that top and bottom. Now, by doing this, I would get one single denominator, x plus 1 and x minus 2. And on top, I would multiply across here. I would get, if I multiply this one, 4x minus 8. And then I would do minus 3 minus 3x. And then minus 3 here. And if I were to combine the like terms together, I would get, so I have my common denominator down here, and I would have 4x minus 3x is x, and I have minus 8 minus 3 is minus 11. So this is something that you've done before in a previous class. Combine this together, two fractions together into a single one. Well, now this section here, partial fraction decomposition that we're going to talk about, actually does the opposite. You're going to be given a problem that looks like this, and you're going to take it all the way back to the original one. So the question is, well, why would you want to know how to do that? Well, primarily for calculus applications, particularly the second semester of calculus is where you're really going to go ahead and use this. So basically, doing a calculus operation to this one might be more difficult, and if you take this and you break it down into two smaller parts like that, then the calculus operations become easier, particularly when you're dealing with integrals. So this is the basic introduction to this section. So now that I've taken a look at this, let's look at our three rules. So we're looking for basically ways that we can take this and rewrite it into different fractions. So that has to do with the way the original fraction is written. So with that, we actually have three different rules that we'll focus on for taking something that looks like this and breaking it down into one or more two or more fractions. Okay, so here's the three rules I just talked about. These are rules for how to break down a fraction, how a fraction decomposes. So first thing is this p of x that appears in all these, that's going to be some kind of a polynomial. Okay, so given that's a polynomial, the top really doesn't matter so much. The main thing that matters is what you have on the bottom. That's going to determine how you break each of these up. So the first thing is, if you look at what you have, and if you have the bottom one is made up of a bunch of linear factors, then you want to use rule number 1 to break that apart. So this might be x minus 3, or it could be a plus, it could be x plus 5, something like that. So however many linear factors that you have down there, that's going to be how many fractions it decomposes into. So in fact, what you do is you just put a constant over each of the linear things. Now, I use subscripts here, A1, A2, and so forth, but you could use A's, B's, and C's if you wanted to as well. It doesn't really matter what letter you use. The main thing is you'll have one constant over each linear factors. So however many there are here, that's how many fractions that you're going to have. If I wanted to take that example problem I just worked through that initial problem and took it down to a single fraction. If I wanted to go the other direction and write it as a sum of two fractions, well, then that would actually be using rule number 1 there. And if you notice, that problem originally started out with two original fractions with linear things in the bottom, and we combine it together into that one. So that's basically rule number 1. Now, rule number 2 happens if you have a linear factor again, but the linear factor is being raised to a power. So maybe you might have x plus 1 to the 5th power, for instance. Okay, so something like that, what you do is you start with the constants again and again. If you want to use A's, B's, and C's, that's okay. So A1 over the first linear factor, and then you're just going to keep going up by 1 all the way until you reach the power of n. So this is a square, third, fourth, fifth, sixth, however many of those that you have. You keep going all the way up until you reach whatever power n is from the original one. So n is here. You'll go up to reach n over there. Okay, so that's going to be rule number 2. Now, rule number 3 also has something raised to a power of n, but instead of having something linear inside, instead we have a quadratic. And that quadratic specifically is one that cannot be factored, because if I could take something like this and factor it, well, then I would have a combination of rule 1 and rule number 2 there if I had that, and I could use that to decompose it. This is where you have a quadratic that cannot be reduced anymore, so it cannot be factored. That's what we mean by irreducible. So if you have that, we're still going to do the same thing on the bottom. You start the one bottom to the first power, second power, third power, fourth power, all the way till you get to n. So much the same as rule number 2. Now the difference is, if you have an irreducible polynomial down there, you're not just going to have regular constants. You actually have an x up there. So actually you have a linear thing written across the top of each of those instead of just a number like these other two cases are. So a1x plus b1, a2x plus b2, a(n)x plus b to the n, however many that you have. And again, you could have a, b, c, d, e, f, and so forth if you wanted to as well. The most important thing is you got an x on top of each of those. That's what makes this one different than the other two cases. So now we've looked at, these are all 3 different cases, 3 different rules. So in this section we're going to first talk about some example problems where we're just going to set up this only. We're not going to actually solve and get the different variables. We're just going to do a setup only. And then once we get done with those problems, then we'll take a look at actually decomposing, where we actually find out what the values of a1, a2, and a3 and so forth are.